Hello, science fans. Today, we're diving into thermodynamics, the science of heat and power. It's all about how energy moves and changes form, powering everything from engines to refrigerators. Mechanical engineers use thermodynamics to design efficient machines and systems. Every action, from running to powering a city, involves energy conversion, guided by thermodynamic principles. Why does this matter? Because energy isn't created from nothing. It's transformed, and efficiency is key. For example, a car engine turns gasoline's chemical energy into motion, while a power plant turns heat into electricity. The rules of thermodynamics help us solve the puzzle of efficiency. Today, we'll unlock a core concept, entropy, and the second law of thermodynamics. Let's tackle entropy, a measure of disorder or randomness. Imagine your clean room, everything in place, low entropy. Over time, things scatter, entropy rises. In science, entropy describes how energy spreads out in a system. Picture gas molecules in one half of a box, ordered, low entropy. Remove the divider and they spread everywhere, high entropy. The more ways molecules can be arranged, the higher the entropy. Think of a shuffled deck of cards, countless arrangements, high entropy. Perfect order? Only one way, low entropy. Nature favors spreading out. Systems move toward higher entropy. A drop of food coloring disperses in water, spreading energy and matter until it's uniform. Maximum entropy. Entropy isn't just disorder. It's about how energy and matter disperse. This tendency to spread out drives countless processes in the universe. It's a fundamental force shaping everything from mixing drinks to the fate of stars. Entropy is the universe's way of moving from order to randomness. Now, the second law of thermodynamics. In any isolated system, total entropy always increases or stays the same. It never decreases. This law gives time its direction. Why eggs scramble but never unscramble. Why heat flows from hot to cold. When you burn wood or watch a building crumble, order turns to disorder. Entropy rises. Even cleaning your room creates more entropy elsewhere, like burning calories or using electricity. The second law says, while you can create local order, the universe as a whole always gets messier. Every real-world process increases total entropy, a cosmic trend that can't be reversed. Entropy is why processes are irreversible and why the universe moves toward greater disorder. It's the ultimate rulebook for how energy flows and changes. For engineers, the second law sets the limit on machine efficiency. Take a car engine. It converts heat to work, but some energy must always be lost as waste heat, thanks to entropy. A perfectly efficient engine is impossible. The second law forbids it. Engineers battle entropy by improving combustion, reducing friction, and using advanced materials to boost efficiency. Every gain saves fuel and reduces impact, but waste heat is unavoidable. Refrigerators seem to defy the law by moving heat from cold to hot, but they use energy to do it, creating even more entropy overall. The maximum efficiency of any engine depends on the temperature difference between its hot and cold parts. That's why power plants run at high temperatures, to squeeze out more useful work. Entropy defines the ceiling for all machines. Understanding it helps us build better technology. Working with entropy is the key to engineering progress. To grasp the second law, consider reversible versus irreversible processes. A reversible process is a perfect theoretical idea. Real life is always irreversible, always generating entropy. Mixing milk into hot coffee, you start with order, end with a uniform, mixed drink, higher entropy. You can't unmix the milk and coffee or return them to their original states without expending huge energy and creating even more entropy. Everyday actions, mixing, heating, burning, are one-way trips to higher entropy. The The second law is why these processes can't be reversed. Entropy ensures the universe moves from order to disorder, from concentrated energy to spread out randomness. That's the profound, practical secret of thermodynamics in your cup and everywhere else.